Let's take a look at these two grids and see what they mean. For the grid on the left, how many rows are there? Let's go ahead and count them. We have 1, 2, 3, 4 rows, okay? 4, right? How many columns do we have? 1, 2, 3, right? You guys know that if you multiply the rows by the columns in a grid, you get how many actual squares are in there. So we have 12 squares, and just to verify for this first example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Alright, let's look at the grid on the left. How many rows do we have? We have 3, right? How many columns do we have? We have 4. So we have 3 times 4 equals 12, right? And just to verify for this first example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's look at another pair of grids. How many rows does the left grid have? 2, right? Columns has 4. How about the grid on the right? 4 rows and 2 columns. Okay, we're starting to see the principle that we're trying to get at here. If we take 2 and multiply by 4, it's the same as if we take 4 and multiply by 2. In other words, either way, we get 8 total squares. This last one's really easy. We have 6 rows on the left, followed by 1 column. And on the right, we have 1 row, followed by 6 columns. In other words, 6 times 1 is equal to 1 times 6. They both give you 6 total blocks. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And now for my personal favorite example, let's look at the top and bottom and compare the two. And these are actually, what I drew here was a simple illustration of baskets of apples. Not a very good one, but it'll work nonetheless. Let me ask you guys something. How many apples are in each basket on the top? Let's go ahead and count them. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And how many baskets are there? Well, on the top we actually have 3 baskets, right? The way we would write this is 3 baskets times 5 apples. What number does that give you? Does anybody remember? Should be 15, right? Now what do we have on the bottom? How many baskets do we have? Well, on the bottom we actually have 5 baskets. And how many apples are in each basket? 3, right? And if we counted all that up, how many apples would we have? We'd also have 15. In other words, if we have 3 baskets and 5 apples in each basket, that's the same as if we have 5 baskets and 3 apples in each basket. The property that we're talking about here is called the commutative property of multiplication. It simply means it doesn't matter which order you multiply two numbers, you end up with the same exact number. And we're going to see that you don't actually have to count that. Okay? In other words, if we had, let's say, 1 trillion times 1 billion, we don't need to actually multiply that to know that 1 trillion times 1 billion is equal to 1 billion times 1 trillion. It works for any two numbers, and we're going to see that in the following examples. Alright, let's take a look at example 1. 7 times 4 is equal to 4 times what number? Okay? Let's go ahead and take a look at the grids again, just so we can have a clear understanding of what's going on. The grid on the left, how many rows are there? 1, 2, 3, 4, 5, 6, 7. So there's 7 rows. How many columns are there? 4. Okay, 1, 2, 3, 4. So it's 7 times 4. On the right, we're actually going to have 4 rows by 7 columns. And if you count all that, folks, and multiply it out, you have 7 times 4 on the left and 4 times 7 on the right, and it's going to give you 28 either way. Now, like I said before, it really doesn't matter how big the numbers are. You're going to start to see that you don't need to count it. Okay? You don't need to count every single square. In other words, if you reverse these, if you flip 7 and 4, you end up with the exact same number. So 7 times 4 is equal to 4 times 7. That's the commutative property of multiplication in a nutshell. For this next example, we're going to look at negative numbers. Negative 6 times what is equal to 5 times negative 6. And I went ahead and thought of a little practical example. Let's say you owe $6 to 5 friends. Okay, so you have 5 different friends and you owe $6 to each of them. How much money do you owe total? Well, first of all, debt is a negative number, so you'd actually owe negative $30, correct? Now let's say in a different scenario, you owe $5 to 6 friends. Well, still, you have 6 friends now instead of 5, but in this case you owe $5 to each. Well, that's like doing 5 times 6. You would still actually owe negative $30 either way. So that hopefully will help you understand that it also works for negative numbers. And therefore, I don't know if you've noticed this, the pattern is the numbers in the middle are going to be the same. In other words, negative 6 times 5 is equal to 5 times negative 6. Let's take a look at an example involving fractions. Here we have 2/3 times 1/2 is equal to what number times 2/3? So you might be wondering, does the commutative property of multiplication work for fractions? And if it doesn't, you probably know the answer, but let's just go ahead and take a look at why it actually works. Alright, we have two scenarios, top and bottom. Let's go ahead and look at the top part, which would be up here. So, this part up here. Let's go ahead and look at the cup on the top left. So and by the way, these are cups of water, and I'll explain exactly what this means. So this cup of water on the top left is 2/3 full, okay? In other words, this right here is 2/3 of the entire cup of water. You actually have 4 parts to 6 parts, so that would actually be 2/3, right? So the cup of water is 2/3 full. Now let's say you're cooking, and the recipe, you have 2/3 cups of water, but then you realize you need to take half of that. Okay, so if we look at half, that'll actually just be that little part right there. Okay, and if we work the math out, what we're really doing is we're starting with 2/3 and we're multiplying by a half. And can anybody tell me how much you're actually left with over here? How much is that of the entire cup? Well, if you count, that's 2 parts water, and there's actually still 6 parts total that we've kind of divided the cup into, so you actually end up with 1/3. Okay, let's go ahead and look at the bottom scenario. So here we're looking down here now. For this particular first cup, we'll actually start out with a half. I'll go ahead and label that here on the left. So 3 parts to 6 parts. We have 3 parts water and the rest is empty. So we have half of a cup, right? And what we're going to do actually is we are going to take 2/3 of that. Now you can actually see, since that's 3 parts, it's pretty easy to see that 2/3 of that would just be those 2 right there. Again, the math for that would be we're starting with a half and we're taking 2/3 of that. And again, you're actually going to see that you're also end up with 1/3. Okay, so in other words, if you compare these 2 cups on the right, this cup on top and this cup on bottom, you end up with the same amount of water in the cup. In other words, we've just visually seen why 2/3 times a half is the same as a half times 2/3. And you might be thinking, well, it might work with this, but what if I had, for example, 1/4 of a cup and I took a half? Would that be the same if I started with a half of a cup and took a 1/4 of that? Yes, it would. And we could keep on showing illustrations to show that. And you know what? If you want to see another illustration, just let me know and be happy to show you. Anyways, I showed you that to show you that 2/3 times a half is the same as a half times 2/3. And again, the pattern you can see for the commutative property of multiplication is the inside numbers are going to be the same and the outside numbers are going to be the same. That's just another visual example to show you why it's true. Let's look at example 4, this time decimals. Let's read this together. What number times 9.5 is equal to 9.5 times 2.5? Again, you should start to see a pattern here. If these two numbers are the same, then these two are probably the same, right? But let's actually go ahead and look at another practical example here. Say a carpenter works for 2.5 hours and gets paid $9.50 an hour. Well, guess what? That carpenter is going to make the exact same amount of money as a server that works for 9.5 hours and gets paid $2.50 an hour. Now, we would hope the server would get tips, right? But the point is, they're going to make exactly the same amount. In other words, 2.5 times 9.5 is the same as 9.5 times 2.5. If you don't believe me, you can go ahead and do that by hand or use your calculator. Again, though, we don't even need to actually know how much they made total, right? If you flip the two numbers, you end up with exactly the same number. So in math, we want to get more and more abstract. In this particular example, we're going to introduce the variable, which we've seen before. And again, for a, we can just think of it as a number. It can be any number, 12, 17, 105, negative 40. It doesn't matter. So a number times 9 is equal to 9 times what? In other words, what goes inside of this box? Now, for this particular example, we are going to think about a shape, okay? And we're going to think of it this way. The shape is 9 feet tall by a feet wide. Okay, so in other words, we don't know how wide it is. We're just going to call it a. It could be 2 feet wide. It could be 70 feet wide. In that case, the shape would look differently, but you get the point. Now, if we flip that shape over, it would actually be a feet tall by 9 feet wide. Now, what do you notice, folks? The area, in other words, a times 9 would give you the area, is going to be the same. In other words, 9 times a is going to be the area of the first rectangle. You'll have the same area as if you do, and I know 9 and a look the same, but a times 9 would give you the exact same area. Hopefully that will help you visualize this particular example. This is going to lead us to the next example, which will give us kind of the formal rule for the commutative property of multiplication. For example 6, we have x times y is equal to y times what? And again, we're going to kind of use a rectangle to hopefully help us understand how this particular rule works, because this is kind of the official way that the commutative property is written. Of course, you could do a times b and b times a, but we're going to use x and y in this example. So let's suppose you have a rectangle that is x units tall by y units wide. Now, if you were to take that rectangle and flip it up, what would happen? It would actually be x units wide and y units tall. Now, what do you guys think? Do you think the area of these are the same? In other words, if you flip the rectangle, would it change how much the area is? The answer is no, it wouldn't. Okay, if you do x times y, that's going to give you the area of the first one. And if you do y times x, it's going to give you the area of the second one. Which means x times y equals y times x. And that, in a nutshell, is a commutative property of multiplication. And another way to write that is a times b is equal to b times a.